In previous videos, I have shown you how to integrate using inverse trig functions. And I'm going to do the same thing here, but there's a twist. We're going to have to complete the square. Here are the three inverse trig integral rules that you need to memorize. We will end up using one of these to help us solve this problem. But to be honest, I'm not sure which one we're going to use. I won't be able to really tell until after I complete the square. It's a pretty safe bet that it's not going to be this one because arctangent has no square root in the denominator, and I see the big old square root right here. But, it might be the third one, arcsecant. I do see that we have the x squared in the front, and then we have extra stuff out here, so maybe it'll be this one, but who's to say? Let me just remind you how completing the square works. I've taken this expression that's under the radical, and I'm going to work this out off to the side. Completing the square involves finding just the right third term for this trinomial. And how do I find the third term? I always think the phrase half the middle squared. So check it out. The middle number is -2. So let's write that down. So there's my -2. Now I need to do half the middle, so I'm dividing that by 2. And then I square it. And whatever that is, that's going to be the third number. Well, -2 divided by -2 is -1. I mean, -2 divided by 2 is -1. -1 squared is +1. So that is the number that completes the square. So I'm going to put a +1 right here. Of course, I can't just put a 1 here because I've changed the value of the expression. So I need to balance that out with a -1 immediately. The point of doing this is that if we now factor the trinomial, it will always factor as the same thing twice. Let's see, so I have x squared, so this is going to be x times x. I have the 1 here, so this will be 1 times 1. And to get the -2 in the middle, I would need a -1 and a -1. So notice that this is x minus 1 times x minus 1. I'm going to bring down this -1 as well. Let's rewrite this as x minus 1 squared. What you see here has the same value as what you see here. So let's make that substitution. So now we have this. Let's take another look at those three inverse trig rules. Now we can see just how well this matches the arcsecant rule. As we compare very closely, we can see that u must be x minus 1. So let's let u equal x minus 1, which means that u prime is just 1. So that's really going to change absolutely nothing. What about the a value? Well, here is the a squared, so the square root of that is still 1. So that means a is 1. If we do the u substitution, here's what we get. 1 over u, right, because x minus 1 is u, so we get the u in the front, and then the square root of u squared minus 1. Instead of dx, we will write du. I started to say du over u prime, but u prime is just 1. So that's it. This is now a perfect match for the rule. So we can go ahead and integrate and write 1 over a. Well, a is 1, so really I don't have to write any of that. So I can go ahead and say arcsecant. So we're going to have arcsecant, absolute value of u plus c. I would say u over a, but again, a is 1. So this is so simple that I'm just going to go ahead and substitute the u in right now. and u is x minus 1. So I'm just going to go ahead and put x minus 1. And that's it. This is the final answer. So that's how you can use completing the square to help you transform your quotient so that it fits one of the inverse trig rules.